Hello, ladies and gentlemen, and welcome back. We're looking at question B3 now in this video from our 2016 Canadian Open paper. A hexagon, ABCDEF, has AB equal to 18 centimeters, BC 8 centimeters, CD 10, DE 15, EF 20, and FA 1 centimeter. Very short side there. Angle FAB is 90 degrees, so the middle angle, so it's got the middle letter is the vertex where the angle is, so it's got a right angle at A and a right angle at D, and we know BC is parallel to EF. Determine the area of this hexagon in centimeters. Well, the first thing I'm going to try and do is draw this hexagon at least a little bit. We know we've got a right angle at A, and so A goes to B, which I guess I'll place out here. And AF, that was the short one, right? AF was 1. AB was 18. Yeah, 18, 8, 10, 15, 20, and 1. Okay, and then BC is parallel to FE. So I guess I can sort of draw it like this. So this was the 20. And this was 8, and then the next one was 10, and then 15, yeah. And then D had the other right angle, right? Yeah, yep, D. So I guess we can place D down here. So we get a right angle like this. Okay. Let's make our picture look a bit more pointy. Okay, so we've got our hexagon here, a 10 and 15. And we know that BC are parallel. Okay, so anytime you're trying to make the area, you think, well, is there a formula? And there really isn't a formula for hexagons. There sort of is one for regular hexagons if you know the side length, but not for something like this. So we've got to break this down into more familiar shapes. And, you know, there's a couple ways you might think to break it down. I'm a big fan of using these right angles. Let's not forget our other right angle here. So I might think, oh, could I do, you know, a rectangle like this, and then I guess maybe another rectangle like this. However, I'm not entirely sure, like, if, so this is hypothetical, like, I don't know how accurate my drawing is, but if I can do something like this, great, then we could extend yet another rectangle, and we could probably figure out something to do with these right angle triangles here. But there might be a problem. Because what if my drawing is not accurate enough? What if we have sort of some overlap? We don't want to count extra area. So it's kind of tricky. We could do something like this, and we could still have like a side X and a side Y. And if we solve for X and Y and they're negative, you know, if one of them's negative and the other isn't, we know there's going to be some sort of overlap. But I really want to avoid something like that. So is there a nicer, cleaner way to break this down, hopefully using these right angles? And I think if we use these right angle triangles, very easy to figure out the area of a right angle triangle. This is 1/2 base times height, and this would be 1/2 base times height. But then what have we got left over? Well, these parallel lines here make me think trapezoid. Just sort of a really odd-looking slanted trapezoid, but trapezoid nonetheless. And I know the base and the height. Well, I'm sorry, I don't need to know the base and the height. I know the base and the top, the bottom and the top. But to figure out the area of a trapezoid, I need the height. Now, I don't know a whole lot about this trapezoid. I don't know exactly where I might find, or how I might find a height here. So, you know, we could wrestle with this idea, maybe go back to the rectangles and things like that. But I like this trapezoid. I like the fact that we're using the parallel lines here. But I don't know how I'm going to get the height here. I mean, it looks like this height is parallel to this, but there's no reason to think that. My picture can be off. This is just a sketch. So, there's no guarantee of that. What can we do? Well, I don't know a whole lot about this particular trapezoid. I don't usually try and find the slanted side lengths, but might give us some insight. I mean, these right angles here might be for more than just figuring out the base and the height of the right angle triangle. So what would we have? We'd have square root of 15 squared plus 10 squared, so that's 225 plus 10. That doesn't inspire a lot of confidence, so that's the square root of 325. And what have we got up here? 18 squared plus 1. Oh, 18 squared is 324 plus 1. We're going to have the square root of 325. So, it's not just any trapezoid. It's, I guess, what would you call that? Isosceles trapezoid? The sides are equal. So there's going to be a great deal of symmetry to this trapezoid. In fact, if we draw a better copy of this trapezoid, in order to have these side lengths be the same, root 325 and root 325, it's got to be a great deal of symmetry. So whatever this height is, if we drop it down like this and get these right angles here, we'll have an 8 here, an 8 here. What's left over to make 20 on this side? 12. It's going to have to be divided evenly between these two, so we're going to get 6's here. And then we can get the height here. So 325 root 325 squared is 325 minus the 6 squared. 325 minus 36. Difference of 11, so that would be 289, and that is 17 squared, so we have a height of 17 here. Now that I know the height, we can get the area. So the area is 1/2 base times height of one of the right angle triangles, 1/2 base times height of the other right angle triangle, plus 1/2 height times the sum of the parallel sides. So we'll get 9, 10 divided by 2 is 5. 5 times 15 is 75. 28 over 2 is 14. I don't know what 14 over times 17 is. 8 and a 2. And a 9. So we get 9 plus 75 plus 238. 9 and 75 is going to be 84. 4 and 8 is a 2. Carry the 1. 1 and 8 is 9. Plus 3 is a 2. Carry the 1. So we should be looking at a final answer of 322. Okay. As I say, this is not the only way I think to go about doing the question. If you would like to experiment other ways to cut this up, please let me know. I'm sure there's other ways, but I like the way this worked out. I liked the trapezoid, and I liked that the side lengths came together and gave us that it was so symmetric. Okay, so that's, what was that, B3. Up next will be question B4. I will see you then. Until then, take care.